Yeah, bro, I know it's two stands.
Okay, let's begin.
But I got you right. I got you.
So, these are some examples that we have left to do from last time. Below this line here, it's what we were practicing when we were doing Weierstrass substitution. That was something that was left over from before. You'll notice that this was one of the quiz problems. So we'll actually see what the answer for that should have looked like. Maybe you got it right, maybe you got it wrong. We'll see. But yeah, let's jump into it. So G. Ideas. I actually gave a hint to this one already. It was to use the rational roots there. Did anyone use the rational roots there to figure out how to do this? What did you do? Yeah?
We do like P over Q for the denominator, so you're going to do all the possible.
All right, so you want to factor
Yeah.
x cubed minus 2x minus 4. And your P over Q is what?
The P is going to be all the factors of 4, negative 4. And then the denominator Q is going to be all the denominators of x cubed, which is going to be 1.
Right, so you look at the possible roots, is what you would say. And they will all be of the form some factor of the constant term divided by some factor of the leading coefficient. So possibilities are, the factors of 4 are 1, 2, and 4. And of course the factors of 1 are 1. Right? So these are the possible roots. X equals one of these values. And so what do you do now with those? Yeah?
You plug it in the equation.
Okay, what are you trying to find?
See which one, when you plug in, you see which one equals to 0.
Right, so you plug in all of these numbers, figure out which one hits 0. Rational roots theorem will tell us if you have a root that hits 0, then x minus that number is going to be a factor. You'll be able to factor the quadratic. So, plugging in 1 or minus 1 should obviously not work here. So maybe let's try 2. Does 2 work?
Yeah.
That will give us 8 minus 4 minus 4. 2 actually works. You'll notice that x equals 2 is a root. This means that x minus 2 is a factor. It means this thing would be able to factor into x minus 2 times something else. How do you figure out what that something else is? Long division. So x minus 2, and we know how to do this. So it's going to be x cubed. You want to leave a space for the x squared, so it's plus 0x squared minus 2x minus 4. Okay, what do we do now?
Divide the x cubed by x.
Right, you get it?
X squared.
What do we do with that?
And then you multiply the x squared with the left.
Right, so x squared times this, you get x cubed. X squared times that, you get minus 2x squared. Subtract this from the top, the x cubes kill each other. Here you get 2x squared. X into 2x squared goes plus 2x. Take that, multiply everybody, you'll get 2x squared minus 4x. Subtract that. The 2x squares die. You will have a minus 2x plus 4x. That'll give you 2x. X into the 2x goes plus 2. Plus 2 times this, you get 2x. Plus 2 times that, you get minus 4. Subtract that, the 2x's die. And you have minus 4 plus 4 gives you 0. Now, you should get 0 in this situation because rational root theorem says you should get 0. So you should get 0 here. And what does that actually mean for our integral? How do I apply that here? What does it mean that when I divide that by x minus 2, I get that? Huh? Yeah?
Would that make that whole thing another factor?
This is the other factor. It means that the denominator will actually factor into x minus 2 times that. Right? Because remember, it's the quotient, pretty much what you would get here is that your x cubed minus 2x minus 4 divided by x minus 2 is equal to x squared plus 2x plus 2 with 0 remainder, which means you can multiply both sides by x minus 2, and you get x minus 2 times the x squared, blah, 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 right? Times that thing. So what it means that this integral is going to, the denominator is going to factor into x minus 2 times x squared plus 2x plus 2. What about the top? That also factors into x minus 2 times x plus 1. Right? Just cancel. So now you have x plus 1 over x squared plus 2x plus 2. And how do you finish that off?
Use substitution.
Substitution. So if your u equals x squared plus 2x plus 2, this means your du is going to be equal to 2 times x plus 1 x. And so you pretty much end up with 1/2 1 over u du. And so this integral becomes 1/2 ln of x squared plus 2x plus 2. Substitution finishes up. So this was in the section when we were doing partial fractions, but it turns out you didn't need a partial fractions here once you actually did the simplification. And rational roots theorem helps us with that. Factoring cubes can be quite difficult, but every now and then what you can try to do, take the factors of the constant term, divide by the factors of the coefficient, plug in the random numbers to see if you hit 0. If you can get a 0, you're lucky. It means that there's a rational factor. There's a rational root, and you can actually do a procedure like this to simplify it. Let's move on to the other one. Get rid of this. So here's one where we want to actually try the Weierstrass substitution on, because the 3 and the 2 aren't going to play well together for us to take advantage of our trig identities, at least not very easily. So, and this is something you have to know for the quiz. What is the Weierstrass substitution?
Equals tan x over 2.
Tangent x over 2. And in that case, your dx would be equal to what?
2 over 1
1
plus
plus u squared du. Your sine x would be equal to what?
2
What would our cosine x look like?
1 minus 12.
So now you could either derive those based on triangles and SOHCAHTOA on this guy with the double angle formulas, or you could just have that memorized and write those down. But those were the things that you had to fill in on the quiz. So pretty much what we're going to do is we're going to make all these substitutions. So here we would have, well, this is 3 minus, I'm going to replace sine x with this guy. So that's 4u over 1 plus u squared. And I'm going to replace my dx with this guy. So that's 2 over 1 plus u squared. So this is going to be like 2 over 1 plus u squared times the 3. I get 3 plus 3u squared. 1 plus u squared times this, the denominators cancel. I just get minus 4u. And so now I have 3u squared minus 4u plus 3. What can I do with that? Does that factor?
I don't need that. I think the 2 and the 3 outside, and then you say u squared is equal to 4 over 3.
Oh, you mean complete the square. That's what that's called. So you would of course maybe try to factor. Factoring is what I probably think of first. But to get these numbers to work out, I don't think you can get those to work out, right? So I mean, the only options for the squared part is 3u and u, but and the only options for this are 3 and 1. If I put the 3 here and the 1 here, that's a 9 and a 1. Can't get to a 4. If I put a 3 here, well, that's not going to work out because that would mean 3 is a common factor, and I know it's not. So this is not going to factor. So completing the square is probably what I want to do, which means I need my u squared to have a coefficient of 1. So factoring out a 2/3 would probably be what I would do here, and I would have u squared minus 4 over 3u plus 1 du. So this is going to be what? U minus, well, I want half of that, so this is 2/3 squared. And if I square that, I would get 4 over 9. To get a 1, I would need to add 5 over 9. And now, that 5 over 9, kind of annoying, so what I would do is, so this is 2/3 times. I would factor out the 5 over 9 from the denominator, which means it becomes 9 over 5 out here. And what I would have is radical 5 over 3 times u minus 3 over 2 all squared plus 1. I would have all of that. And then, of course, I would do a substitution, because the whole point of me doing that is to make it look like this formula that Jhevon forced me to memorize. At this point, something like t equals radical 5 over 3 u minus, that should be 2/3. Then my dt is just going to be radical 5 over 3 du. And so what I would end up with is 2/3 times 9 over 5 times 3 over radical 5 times, this would be 1 over t squared plus 1 dt, which gives you the arctangent. So 3's would cancel, and I would have essentially now 2 over 5 times 9, 0 5 radical 5, times tan inverse t plus c, and our t was that thing, and our u was that thing, so I end up with 18 over 5 radical 5 tan inverse of radical 5 over 3 tan inverse over 2 minus 2/3. That's the integral. What you guys got? Something similar? You probably simplify the constants a little bit differently, but that's essentially what it should look like. Any questions on that one? So the numbers here were kind of ugly, but hopefully the process is a little bit clear. You get to a situation, my knee-jerk reaction is, well, would a substitution work? But if I make u a t equals this, then my dt is not going to be useful. So instead I would think, okay, maybe I can factor into a partial fractions, but that didn't factor. So then, once it doesn't factor, you think completing the square. Try to get a trig substitution maybe to work out. Or sometimes you'll have a nice little formula that you can take advantage of. So that's that one. Most of the others. What did you guys do for this one? Weierstrass, So our sine x is going to become what? By Weierstrass. So it becomes 2u over 1 plus u squared. What would tangent become?
So u over 1 minus 1.
And dx is going to be 2 over 1 plus u squared. So this is going to look like the integral of 2 over 2u plus 2u 1 plus u squared over 1 minus u squared du. How did you deal with that? Multiply by 1 minus u squared over 1 minus u squared. That's the quickest way to simplify a complex fraction. So it's 2 times 1 minus u squared over 2u times 1 minus u squared plus 2u times 1 plus u squared. And let's clean up the denominator a little bit. 2u minus 2u cubed plus 2u plus 2u cubed. So this cancels that. And so now I end up with 1 minus u squared over, that's 4u. So it's going to be a half out here. So this is 1/2 times, sorry, ln of absolute u minus u squared over 2 plus c. And our u was the Weierstrass substitution. So this is 1/2 times ln of tangent x over 2 minus tangent squared x over 2 over 2 plus c. That's what that one would have looked like. And for the most part, you guys should have gotten something that looks similar to this. At this point, you guys should be pointing out whether I'm making a mistake, not the other way around. Finally, D. Now, this one is probably of high interest since actually this question verbatim on the quiz. I think on one version I rearranged the terms. I really like 1 plus sine x plus cosine x or something. I'm trying to fake some of you on, but it's the same thing. We're just to see, well, I know how to do with sine x plus cosine equals 1, but what do you do with 1 plus That'll be funny if that actually happened. What do I do with the ones in front? Like, you don't do anything differently. Okay, so, all right, sine x, 2u over 1 plus u squared. Cosine x would be 1 minus u squared over 1 plus u squared. 1 is just 1. This is 2 over 1 plus u squared du. That is going to be equal to 2 over 2u plus 1 minus u squared plus 1 plus u squared du. U squares die. I would have 2 over 2u plus 2. All simplifies very nicely. That's the integral of 1 over u plus 1 du. And that's just, ln. Right, so 15-second problem. At least it should take you like 15 seconds if you at least looked at it before. So yeah, this is ln of u plus 1 plus c. And of all these, that was the nicest one to do. Although E would be a very nice thing to ask on a quiz as well.
It's actually almost right.
So yeah, that was supposed to be the answer on the quiz, just in case. So hopefully you got that. Let's. What's so funny? Okay, so here I gave you a hint because I wanted you to do a Weierstrass-esque substitution, but there is a nicer way. Anyone think of a nicer way to do this one?
Double angle formula.
The what?
The double angle. Cosine
Which,
of
which
2x is equal to cosine square minus 1.
2 cosine squared
2
minus
cosine
1.
square minus 1.
Right, so a nicer way to do this would just be apply the double angle formula. So this is 2 cosine squared x minus 1. Ones would cancel. So you essentially get 1/2 times integral of secant squared x dx, which is 1/2 tangent. So that would be like a quick way to do it. Like if you weren't forcing me to do a Weierstrass, that's probably what I would have done. But I guess I wanted you to go through just the idea of manipulating the formulas to figure out, just for you to redo the process that would have given us the Weierstrass substitution. And so let's just run through that just for the fun of it.
I didn't really get my extra
Yes.
5. I think I'm
Okay,
telling
just
it's
sit.
about the extra time on the quiz. Like I
I
didn't get
understand. Please sit down and be quiet.
it's about any extra 5 minutes for the quiz. Actually, because accessibility didn't get a chance to give me extra 5 minutes.
Talk to me about it after class, please.
So about me finishing the quiz.
Okay. So with the u equals tangent substitution. Now why u equals tan x instead of tangent x over 2? Well, it's because we have a double angle here. So I just pretty much decided to double up on the Weierstrass substitution, which you can do. So and this is just also showing you a new technique that you can try. So it was like cosine of 5x, in which case don't have this to help you out. You could actually do a tangent substitution like 5x over 2 or something like that. And that would actually work out nicely. So given that, basically this means you can create a triangle where there's an x here, and tangent is opposite over adjacent. So this side here is going to be 1 plus u squared, square rooted. So this means that your, what do we want, sine of x is going to be opposite over hypotenuse. It also means that cosine of x is going to be adjacent over hypotenuse, which means my cosine 2x is going to be, well, cosine squared x minus sine squared x. So I'm going to square this, I'm going to get 1 over 1 plus u squared. I'm going to square that, so this becomes 1 minus u squared over 1 plus u squared. It's going to look very similar. Also from this guy, I would get, well, x equals tan inverse of u. So my dx is going to be 1 over 1 plus u squared u. So you won't get 2 over, you get 1 over. But other than that, it's pretty simple. So this means our integral would become cosine 2x is this, 1 minus u squared over 1 plus u squared times 1 over 1 plus u squared. And this will be 1 over 1 plus u squared plus 1 minus u squared du. And at that point, that's just a half. So this is u over 2 plus c, which gives you tangent of x over 2 plus c, which you'll see it's the same answer. Of course, you went through a lot more pain. And this is typical for a Cal 2 integral. You'll often have several ways to do it. Another way to do this, you could actually multiply by 1 minus cosine 2x over 1 minus cosine 2x, and then do a substitution for sine 2x. That could also work. But yeah, multiple ways to do this integral. This is by far the easiest way. That's probably the way I would have done it. Okay, finally, secant x. Let's get through this one. So I just wanted you to experience another way to do this integral. So we already know the answer here. What's the integral of secant x? Right, so we know that that should be the answer, okay? We derived that by other means, and it was kind of mysterious the first time we actually did it. We multiplied and divided by something that seems totally random. And yeah, after we did it, we kind of saw, oh wow, that's really convenient how that worked out, but who would have seen that in the first place, you know? Weierstrass substitution, though, actually gives you a direct constructive way to actually find this. So once you learn about the Weierstrass substitution, I feel like attacking this with a Weierstrass substitution would be a more intuitive way to actually go about solving the problem than multiplying and dividing by this mysterious expression. So, that being said, we would set our u equals tangent of x over 2. And this would give us, basically this is 1 over cosine. And our cosine we know is what? 1 minus u squared over 1 plus u squared. And our du is 2 over 1 plus u squared. So this will give us 2 times 1 over 1 minus u squared du. So it becomes that. How would you do this? Huh? In factor.
Partial fraction.
Right, you can use partial fractions with the cover of method because you have non-repeating linear factors. So, remind me how that works again? How do I find out what's on top of here?
You make u equal to 0.
Why u equals 0,
I mean, the denominator equal to 0.
right? Which means our u would be?
1.
And how do I apply that?
Cover up the
Cover up that and plug in u equals 1. So, a half would go on top of that one. And u equals minus 1 would make that denominator 0. Cover that up, plug in u equals minus 1, and you get what? You get a half again. Of course, the times the 2 is going to kill the halves, but we would end up with what's the integral? Right, these guys are all there. ln?
1 absolute value. 1 minus absolute value 1 plus 2.
No, something is off. Negative in front of this because of the negative in front of that, which technically you have to do a substitution to do that. T equals 1 minus u. Your dt is going to be minus du. That's where that minus sign is going to come from. Now, plugging in our u, this is minus ln of 1 minus tangent x over 2 plus ln of 1 plus tangent x over 2 plus c. And the follow-up question is, well, that looks hella different from that one. How did you justify to yourself that this actually is a valid answer? Did anyone do that? How do you go from one to the other one? good? Yeah,
So I kind of just stopped at the ln of one ln of 1 plus u over ln of 1 minus u, and then I just kind of multiplied by the I want to say the reciprocal, and then just kind of tried to get something that would look like secant and tan in terms of the substitution. So
Okay. So you started here?
yeah, so then I just rearranged that so that it looks like ln of 1 plus u over 1 minus u. And then I multiply by the negative at the bottom. So
Well, yes, that's true by log rules. And then what did you do?
and then I multiplied by 1 plus u, top and bottom, and then expanded.
1 plus u, you multiply top and bottom. So that's going to be 1 plus u squared on the top. So that's 1 plus 2u plus u squared. And on the bottom, you would have 1 minus u squared.
Correct. And then I kind of rearranged some of the terms and then just kind of separated them into two positive.
Okay, and then
So, for example, I kind of I had two separate fractions. I have 1 plus u squared over 1 minus u squared plus 2u over 1 minus u squared. I broke up the fraction basically, or yeah. And then those should translate to that if you were to do, because secant's 1 over cosine.
right. Notice that this is 1 over cosine,
Right.
actually. So it's 1 over 1 minus u squared over 1 plus u squared. And that one is actually what?
That should be tangent, but the denominator should be 1 minus u squared.
Okay, so how did you fix that part? So you're gonna get your secant here. Oh,
Yeah, sorry, yeah, so that one should technically just be
so that's
the ratio.
also, that's straight up a tangent, right?
Correct.
So this is straight up like, yeah, so this
It's
is.
like algebraic manipulation, I guess. That's
Yeah.
what you call it.
And this is 1 over cosine, so that's actually just ln of secant x plus tangent x. So they're actually exactly the same thing. They're not even off by a constant, which is interesting. That's probably a harder way to see it. That does work. I probably, at this point, I would have had this, I would have plugged in the tangent x over 2. Probably write it as sine x over 2 over cosine x over 2, multiply top and bottom by cosine, and it's going to be easier to see how to get the formulas there. But yeah, they're the same. This one is a little bit more constructive. I thought it'd be interesting for you to see that. Okay, now let's move on to the next phase. So, I would like to do a summary of all that we've learned over the past few weeks. So, I meant big part of Calc 2, the first third of the class is all about learning how to integrate, the fundamental techniques of integration. So, I want to complete the integral strategy for you. So, let's put together all that we've learned. Let's become masters of integration now. Where no calculus 2 integral is going to be safe, I mean, integrals from other classes might still be out of your reach, sure. But no calculus 2 integrals should give you problems now. Now that we've seen everything that you would need to know. So, let's actually go back to integration strategy, the art of integration. Okay, so faced with some integral of f of x dx, how do you go about computing it? What should go through your mind in roughly what order? What are the things you would look for to know, oh, I'm going to apply this technique, or I'm going to try this, or I'm going to try that? It should not be at this point. I mean, sometimes it will take trial and error, but at the end of the day, you should kind of know what to look for to the point where even when you're doing trial and error, you would tend to go in the right direction as a first or a second step. How do you actually approach some random integral, right? And by the time you get to the test and of course the final, that's kind of how it's going to feel. There's going to be a problem on my test, there's going to be a problem on the final where the point of the problem is just having you solve a bunch of random integrals. Problem 1, parts A, B, C, D, solve all these integrals. They aren't going to give you any hints, nothing. You just have to know, what am I looking at, how do I tackle this integral, right? So, faced with some random integral you want to compute, step 1. What was step 1?
Basic rule.
Right, try to apply a basic rule. So these are the guys that Jhevon asks you about on quiz 1 all the time, on problem 1 of any quiz. The basic rules. So these are guys like integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. When your n is not equal to minus 1, if your n equals minus 1, it's 1 over x dx. It's ln of absolute x plus c. Integral of secant is ln of secant x plus tangent x plus c, etc. Right? Now, in a Calc 2 class, I'm pretty much never going to give you an integral where step 1 is going to be all that you need to know, but appreciating step 1 is like a big part of integration strategy because not only are these basic rules, you want to think of these as your templates. They are your lighthouses in the darkness, right? Every time you have something that does not look like this, your first goal would be, how do I manipulate what I have to make them look like one of these guys, right? Every time you take a step on some weird, crazy integral, your goal is going to be, how do I make this weird, crazy integral look like something that a step 1 process could look like, right? You're always thinking of that formula of how you can manipulate things to look like one of these guys. And pretty much what all the other strategies were exactly that. Substitution by parts, all of that. It's all to break down an integral where it's going to end up looking like one of these guys where you can just apply a basic rule. So it's very important that you know them, even though you're not going to directly just use it to solve an entire problem at this level. To know how to solve a more complicated problem involves knowing how to use algebra and strategies to get to this situation when you're not given it initially. So, very important step. Just knowing the basic rules automatically gives you a lot of power, gives you a lot of insight, gives you a lot of things that you know you might want to try. I know I can try this manipulation because it's going to make it look like this thing. So, step 2. What was step 2? Try to simplify to do what? To look like a basic rule. So again, step 2 is basically try to use algebra to get to step 1. Simplify to look like a basic rule. Right? So random example there. X squared plus 2x plus 5 over x cubed. Right, so the idea is, well, that doesn't quite look like one of these guys, but I can easily get them to look like, well, the rule over here by just dividing everyone by x cubed. Now these guys I can rewrite. This is just 2x to the minus 2 plus 5x to the minus 3. So now I can simplify it so that the last 2 terms look like this rule, and the first term looks like that rule. So now I can solve for that. So that's going to be ln of x minus 2 over x minus 5 over 2x to the minus 2 plus c, right, as an example. Right? Just a random, silly example. Step 3, what is the third thing you always think?
Substitutions.
Try substitution. Now these are always the first 3 things that you will think about. One thing I want to say, again, I've said this before, but just to re-emphasize, this is not your Calc 1 garden variety substitution anymore. Sometimes you won't find the du factor present in your integral. Right away, right? So, for example, you see an integral like this, e to the square root of x dx. It turns out that a substitution is what the first thing you want to approach that. Now, of course, if you let u equals the radical of x, your du is going to be 1 over 2 radical x, which you don't immediately have a 1 over 2 radical x dx. Ways that you can get around that, again, algebraic manipulation. I can multiply by 2 radical x over 2 radical x. And then there's going to be my du. And then, of course, this is just going to become 2u e to the u. So this will be 2u e to the u du, right? And that you do by parts, right? So the initial step of the substitution might not be an obvious one. We did another example where we had like a 1 plus x squared over x, and it turns out you could do that by substitution. Letting your u squared equals this guy, of course your du is not exactly present, but by multiplying by x over x, you now make it present, right? So you should be aware that sometimes the substitution is not going to be your Calc 1 obvious kind of substitution. Sometimes you might have to do a certain manipulation to get it into a situation where substitution will work. But it's worth your time to actually do this if at all possible. So you should always consider, can a substitution work? The other principle of substitution that you made from Calc 1, that still holds true all the time. You are trying to substitute something to make the integral simpler. What does simpler mean? Looks like a basic rule. Get back to step 1. You're always trying to get back to step 1. Knowing that you know a rule like this kind of tells you, well, you know, I know how to deal with just the variable. I don't know how to deal with the square root of the variable. So your initial idea might just be, let's make that just a variable without a square root. Why? Because I have a rule for that. So what you're going to try to do is just try to do a substitution that's going to make it look closer to one of these guys, and then try to see if you can work it out. And sometimes you will be able to do that, like on these integrals, where it's not obvious initially that the substitution is going to get to work out, but you should always consider it and realize, can I manipulate it some way to get the substitution to work out? I'm not going to talk much more about substitution because you guys should have had that handled since Calc 1, but that's just an initial thing. Always the first 3 steps when you're faced with a random integral. Probably not going to work out with an integral at this level, but knowing these rules is indispensable. Not knowing the rules, you're going to feel lost. Things that are going to seem random to you. When I'm writing out solutions on the board, you might understand them in hindsight, but you're not really going to know how to do them on your own. And usually if you're in that situation, if you understand what I'm doing, but then you're in a situation where, you know what, I would have never known to do that. I saw what he did. I get why it works, but I feel like I wouldn't know how to do that if I was in his position. Step 1 is where you're falling down, right? You don't know the rules well enough. Okay, so now, the above are always done in that order. The following are not necessarily done in this order. Right? So I'm just going to give you roughly the order in which we covered the techniques, but it's not really an order per se. So what would a step 4, quote unquote, look like? So it's not really a step 4. It's not always the 4th thing you think about, but just to have like some number system going here. Step 4, int by parts. This is another technique that we learned about, right? So you're faced with a random integral, doesn't look like a basic rule. Can I simplify it to look like a basic rule? Will a substitution work? Okay, assuming none of that works out, right? So you would not reach step 4 or any later step until you already tried the first 2 steps. So for the rest of this time, we're assuming that a substitution does not directly work out. Okay, integration by parts is another technique we learned about. Why would you choose this technique? How are we looking at a random integral? Why would you know? You know what, integration by parts is probably a good thing to actually try here. So, particularly useful. If 1, you have a product two different types of functions. Okay, so you're looking at an integral and you realize, oh, it's an exponential times a trig function. Or it's a polynomial times an exponential. Or, right, you have two different types of functions. You have an e and a t. Or you have an a and an e, right? Once you're looking at an integral, you already tried step 1, 2, and 3 and it's not working out. But you notice, hey, there are two different types of functions here multiplying each other. Integration by parts might be a good thing to try. That's one of the things that would indicate to you, hey, integration by parts might be a technique I want to try, right? So whenever you're doing integration by parts, it's not because, let me try integration by parts. No, you're seeing something specific which is going to make you want to try integration by parts. One situation is you have two different types of function multiplying by each other. Another situation, why would integration by parts be useful? A second very common situation. It's usually one, but technically you could have more. You have one function whose derivative is easily computable. And it would be useful in an integral. Especially if multiplied by an x. For example, it's an integral like that. You don't have a product of two different types of functions. Step 1, 2, 3, not going to work out for you. But you realize, hey, I know how to find the derivative of tangent inverse. It's 1 over 1 plus x squared. And I know that if I made my u the dx, I'm going to get x times 1 over 1 plus x squared. Right? So you realize that by parts, it's going to give you something, it's going to give you something minus the integral of x over 1 plus x squared. Right? That's super convenient, right? The derivative of the function is more convenient to have in the integral than the function itself. Whenever you notice something like that, integration by parts might be a good idea. Right? Now, we have looked at, so those are the two more common types of situations. Why would I choose integration by parts? Chances are you're going to choose it because I have two different kinds of functions. Or, you know what, I'd rather have the derivative of the function than the function itself, right? If you see some of those ideas, then you're going to say, hey, let me pick u to be that function, my integration by parts. There are other situations, and at this point it's kind of a toss-up. So, for example, we looked at the integral of secant cubed, which the standard way to do that integral would be integration by parts, where you'd actually break it up into this, where notice that it's not really two different types of functions. This is a t and a t. However, it does kind of fall into category 2, where you realize, you know what, the derivative of one of these is going to be convenient in the integral, but it's not, probably not clear-cut one of these two types, but there are others. There are other times when it might not work, so this wouldn't work. So it's something to consider, but probably there are situations that could be very similar. Like, I can do integration by parts here with these two very same types of functions, but if I actually integrate, like, say, sine 5x, cosine 3x, and you tried integration by parts, it actually wouldn't work out for you, even though those are two trig functions, again, right? It wouldn't work here. You'd actually get like a 0 equals 0. It's not going to be very convenient. So again, it's not Calc 1 anymore. There are nuances here. There's kind of an art to this. But integration by parts, good thing to try if you're in one of these two situations. And if all else fails, other than all the other steps I'm going to tell you, a desperate ditch effort might be to try something like this. Break up the function and try an integration by parts. Break it up into a situation where a part of it you can integrate easy and a part of it you can differentiate easy and see what you get. But yeah, that's what an integration by parts might be. Yep.
In a note, I have the says the integral of e to the x squared dx is, does not exist. Is that a true statement?
E to the x squared,
Ex squared.
e,
I mean, I'm
Raised to
sorry,
the x
e to
squared,
the
yeah.
x squared.
yeah,
Double.
has no antiderivative.
Okay.
Right. Right, that is correct. Other common ones, sine of x squared, also no antiderivative. Cosine of x squared, or x cubed, or anything other than an x, also no antiderivative. So yeah, that would kind of hint you. So if you saw something like the integral of x cubed e to the x squared, and you're like, oh, I'm going to try by parts because it's two different types of functions. You need to know that the e to the x squared could not be one of the parts. It's not going to work out for you. So what you would do first is a substitution. Substitute that first, then try to apply the integration by parts and what results, right? So you should already have some idea of certain things that can't work out. So that would also give you some insight into how to apply the integration by parts. Sometimes you might have to do a substitution before you can actually apply that. But yeah, that's when an integration by parts would be useful. And I assume you guys all know about integration by parts, so I'm not going to teach it again. This is just when you would think about trying. But yeah, these guys, they do not have antiderivatives in the conventional sense. In later classes, what we kind of do is we kind of just make up functions that we define to be the answer, but it's not really an answer we can actually write down in ways that we understand. Kind of like how complex analysis was invented when you, let's pretend the square root of -1 has an answer, and then you get complex analysis, same kind of idea. You can just pretend this has an answer that you call the ERF integral, ERF function, the error function, and that's outside of our pay grade at this point. Step 5. Trig integrals. So our trig identity is useful. So you see like a sine to some power times a cosine to some power. I'm talking about those kind of guys. You saw things like that. Or you had like say the sine of x over the square root of 1 plus cosine of x dx. Things of that sort. You have like trig identities that can help you out. Or just knowing a substitution would actually be what you try here. But get the idea. Using trig identities, will they help out? Kind of a step 5b is trig substitution. When is a trig substitution going to work out?
The numerator is has a positive odd factor. No.
How do you know trig substitution would be something you might want to try?
Is it one of those three cases?
Right. One of these expressions occur. Say an x squared minus an a squared, or an x squared plus an a squared, or an x squared, or an a squared minus an x squared. And here your a is a constant, your x is a variable. It's loosely a variable. Of course, there can be variations on this. So you could have something like 2x plus 1 squared plus 3. You could think of this as just 2x plus 1 squared plus radical 3 squared and apply that idea. So when you have one of these three expressions, especially when they're stuck inside of radicals or other nefarious situations, a trig sub might be something to try. When not to try it. So some notes on the trig substitution. 1, back substituting in the trig substitution can be quite annoying. So what you want to do is always change the limits. if doing a definite integral. With trig sub, always change the limits. It will save you the whole back substitution part of it. 2. You do not need it if you have an odd factor of x. Or usually, so if you have something like x over the square root of 1 plus x squared dx, that's a regular substitution. Or you could have 1 plus x squared over x dx. That you do with a substitution would lead you into an integration by parts, but you don't really need a trig sub once you have an odd factor of x lingering somewhere. So you would not use a trig sub in these two situations. It would tend to be a waste of time. So if you have only even powers elsewhere, like a fourth power or a squared power, that's when I would use a trig substitution, especially if there's a radical in there. So that's when a trig substitution is useful. You see one of these expressions, you try to take advantage of the trig identities with either the secant, the tangent, or the sine function. What else can we look at? Partial fractions. When would you use a partial fractions? So this is when your f of x is a rational function. Whose denominator factors. Right? So do you have a rational function, meaning a ratio of two polynomials, and the denominator factors? You probably try to do a partial fractions. And again, that's assuming that a regular substitution or simplification is not going to work out for you. So we're still assuming that you went through steps 1 through 3. And the notes here is function needs to be proper. And if not, long division or algebraic manipulation is necessary. Right? So there are times when you might have an integral say you have something like x squared over 1 minus x squared. Now you might notice that the 1 minus x squared, you could do a trig substitution here, but again, trig substitution is kind of annoying, has this back substitution part. I would notice that, hey, the denominator actually factors, and but it's not proper. But so what I would do here is I would make it proper. I would say factor of a negative, and then I would minus 1 add 1, and then that would be the integral of 1 plus 1 over x squared minus 1. I would get this is 1, and then this is say x minus 1 times x plus 1 dx. And if I think of this as, say, x minus 1 times x plus 1, if I cover up the x minus 1 and plug in 1, I would get a half. And if I cover it up the x plus 1 and plug in minus 1, I would get minus a half. So that integral is just easy now. It's just x plus 1 half ln of absolute value of x minus 1 minus 1 half ln of absolute value of x plus 1. So I see something like this, rather than going through a trig sub, which is not necessary, it's a rational function. And the denominator factors. Partial fractions would probably be my go-to method. Now, if I had something like, well, this would still be a partial fraction. Not partial fraction. Now if I had something like this, 1 plus x squared, now it's not a partial fraction. Because the denominator can't be factored. How would you apply that? How would you do that one? Yeah.
Would you try completing the square?
No, it's already in a nice form for a complete square. It's already a complete square. No, substitution would not work here. What would you substitute?
Would
Yeah.
you use the trig sub?
You could. That's the harder way, though. There's a much easier way.
Is that one of the rules?
It's not a rule. But I can get it to look like one pretty easily.
Could you think of it as the numerator is 1 times x squared and take out tan? Or am I not thinking?
No.
Times.
Yeah?
You divide everything by x squared?
No? How would that help?
Like,
You get 1 over
Oh, you
1
just-
over x squared plus 1. Yeah.
X over 1 plus x squared is the derivative of arctangent. So, when you have something,
I don't have x. I have an x squared on top.
you can take out, you do x times x over 1 plus x squared.
And then what would you do?
And then by parts.
Too complicated. In simpler grasp. Trig sub could work. What you said. Could it work? Da-da-da. You get an ugly integral at the end of the day. You get like an x squared times an ln or something, which then you do by parts again. Then you'd end up in a situation where you need like a bigger partial fraction. Like, no, that's gonna turn out really crazy. No, definitely not. That's worse than a trig sub, which it's hard to believe that there are very few things that would be worse than a trig sub. Yeah,
oh, you can't do the plus 1 minus 1 thing, right?
you can.
Oh, you could. Oh, so like you would do that then? Like,
Yeah,
really?
that's by far the easiest way. Add 1, subtract 1. You get 1 minus 1 over 1 plus x squared.
Oh yeah.
And those are 2 basic rules. Grasshoppers, think grasshoppers. You know what happened here? You guys forgot step 2? It simplifies into a basic rule. Why would you, oh, trig sub or integration by parts? Don't forget the strategy. Right, we already saw, and in fact, I literally just did it, something very similar right beside it. Like you should have saw, oh, I can just kind of simplify that in a similar way, right? Yeah, and you have the arctangent right there. Right, me seeing that 1 over 1 plus x squared is going to make me think arctangent, because without the radical there, like, if there were a radical, then yeah, trig sub for sure. What else would I do? Without the radical, now I have options. That's a rational function. Partial fractions might be what I would think, but then I'm like, denominator doesn't factor. What do I do? Well, there is a thing I know about 1 over 1 plus x squared, because Jhevon forced me to memorize it. Can I get that here? And easily you can. That's the much simpler way to do it. So yeah, partial fractions. So you guys did say some things that would work out, but it would take you a lot longer, and a lot of the time is of the essence here. So you don't want anything too complicated. Step 7. So this is the Weierstrass substitution. We did a lot of examples in this class, so I'm not really going to talk about that, about how to do it anymore, but just notice this is when your f of x is a rational trig function. So it looks like and trig identities don't help. Right, so we did an example today, say sin x plus cosine x plus 1. It's hard to get a trig identity to help you out here. You might have to multiply and divide by something very exotic, but by the time you figure out something very exotic, you would have already solved it, the full problem by a Weierstrass substitution, right? So you have a rational trig function, and your trig identities don't really help you out. And of course, this is assuming that you have to know all your trig identities, half and form, double and form, sine squared plus cosine squared is 1, etc. So, one thing that students sometimes mix up if they don't study enough, and hopefully no one is in that boat, is you do a trig substitution when you don't have any trig, and you turn it into something with trig. The Weierstrass substitution is literally the opposite. You have something with trig, and you transform it into something that doesn't have trig. And when it's a rational trig function, it'll usually transform into something where you could do partial fractions on it. And that's everything. Those are all the fundamental integration techniques. And these guys will be useful for as long as you're alive and integrating. Even when you go to higher classes and you learn all these sophisticated techniques and theorems to apply to integrals, at some point, you're going to boil those problems down to situations that will fall into one of these 7 categories. And if you really want to be minimalistic, you could realize that there are really 2 ways to integrate something. It's a substitution or it's an integration by parts, right? Weierstrass substitution, trig substitution, they're all substitutions, really, right? So substitution as a broad category and integration by parts as a broad category is how you're going to kill any integral. And the strategies are really just helping you to transform the integral into a form where you can see a nice substitution or an integration by parts, or maybe even a basic rule if you're lucky. So you need to know the basic rules, and the strategies are just about transforming that ugly mess that you're looking at to look more like a basic rule. And yeah, these are when you would kind of approach a particular integral. So you want to look over that, make sure you go through the strategy, read it, make sure you understand it, make sure you know what to look for when a certain strategy might be useful as opposed to some other strategy. And yeah, so how you would go about doing it. Did you have a question?
Oh, there was a question about the quiz, basically. I mean, like, I think there's one more question I need to double check the accessibility. You know, like 5 minutes to double check, like, you know, and that, therefore I can give you back the quiz. Like, I didn't get a chance to finish it, actually.
Well, that's not a general question about what I'm talking about. That's a very personal question. You should address, ask me at the end of class. Other questions about what I spoke about, the strategy. So in general, again, you see a random integral. There are 3 things that you should think about in a particular order every single time. Basic rule, can I simplify it to be a basic rule? Can a substitution work? Other than that, there are cues that's going to tell you when one of the other 7 guys can actually work out, right? 2 different types of functions, or the derivative of something is going to be useful. Integration by parts might be your guy. If you have a rational trig function, a Weierstrass substitution might work out. If you have the x squared minus a squared, right? Everything that I already explained, I just explained. Okay. So that's kind of when they're going to work out. So what you're going to do now is you're going to do all the homework. You're going to practice a lot of problems. You're going to get really used to these things. Make sure you actually know how to apply all the techniques I told you. Now, eventually, what you're going to want to do is practice more than you can possibly actually practice, right? Because that's how you're going to get good at integrals. And then you're like, how do you practice more than you can actually possibly practice? What are you talking about, Jhevon? We expect the unexpected. No, here's what I mean. Let's actually do an exercise. So, I'm going to share a little pro tip with you guys here. So it's a lot of pages, so I didn't make a copy for everybody. But I'll post an electronic version of this on the website soon. So you guys are pretty much going to have to double up, get cozy. You should actually know one other person in the class anyway. So double up. I'm going to teach you guys a pro tip. So it turns out, when you want to progressively overload all your math practice, how do you actually go about doing it? Well, a pro tip is you are going to want to somehow play a math game. Like one of the ways I got good at math and how a lot of my friends got good at math is we'd often have these little math games or challenges between each other. Now I'm going to tell you Sounds geeky, but it works. Like if it works, don't knock it. Okay, so I'm going to tell you about a kind of game that is particularly useful when it comes to figuring out how to kill integrals, right? So here's the idea. After you do all the practice and you know how each technique works and what situations it would be useful, what you're going to do is you are going to do, as I did for you here, you are going to go through a few calculus textbooks, including your own, and just group all the possible integrals that you can find. Like at this point, I took this from like 3 different calculus textbooks, just like have a bunch of integrals, like hundreds of them. You're going to group them together, right? And here is the challenge. Integration, by the time you get to an exam, it should be one of those things where it's like, the battle is won in the mind. You know, it's like really kind of cheesy. But you should know how to do an integral within a few seconds of actually looking at it, right? You writing out the solution should be a formality. It shouldn't be like, you shouldn't have to think about it really, right? So what you're going to want to do to make sure you know how this integration game actually plays, you are going to get a bunch of integrals. And you can even challenge a friend. Make it fun. Like, put some skin in the game. Like, okay, who gets the most of them right? If I get more, you buy lunch, right? You make it fun, right? So here's how the game is going to play. You are going to look at a random integral, or have your friend pick a random integral. Pick a number on the page. The goal is to actually talk about the answer in 3 to 5 seconds. I'm not kidding. Literally 3 to 5 seconds, okay? You should look at an integral, and within 3 to 5 seconds, you should know exactly what you would do to kill that integral, right? The rest is a formality. And the more you do this, it might sound impossible to you guys near, I'll probably tell you a story next time about something like this, but it might seem impossible to you now, but trust me, within a week, you can get that good. Like, I can look at an integral and in 5 seconds, I know what I need to do. And because you already went through the homework, you have the skills to pull it off. So not only can you see what to do, you have the skills to actually do it, right? So you need both components. One or the other is not going to work. So going through your homework is going to give you the skills, but now you want to practice the mindset to actually see it. So that's what we're going to do now. I'm going to pick random integrals from this page. You guys are going to tell me how to attack that integral in, let's be nice. It's your first time playing this game for a lot of you. Let's do 5 seconds. Okay? All right. So I label the pages on top. Let's actually do this. Page 3, problem 11. Okay, you guys pick. All right, moving on. Page 1, problem 1.
Substitute.
No, wrong. Okay, page 1, problem 10.
Trig substitution.
No, wrong. It can't be a trig sub. There's a tangent there. Trig sub does not work if there's already trig. Okay. Page 1, problem 41.
U sub.
What would you substitute?
U equals 2x.
All right. See that? That's what I want. Right, he like 2 seconds, he got you sub, dude. All right. Page 2, problem 53. What is the trig sub?
A squared minus x squared.
No, tell me specifically the trig sub.
Which is sine.
What? X equals 3 sine theta. 3 sine theta. Okay. Problem 69, same page.
69. Trig sub? Trig sub?
No. Okay, you guys got it wrong. Moving on.
Which one is
Page 4, problem 31. Or you guys are dead. Page 4, problem 71.
Oh,
You
that's
sub.
2.
You sub.
What would you substitute?
The x.
2x.
No.
Oh, yeah,
No.
it's x.
Then how is that going to help? You're going to get an e to the u over 2 in the denominator, and it doesn't look any nicer. Problem 56. Same page, page 4.
Algebra. Algebra? That's what you said. No, that's not the point.
The parts? We're dead.
Integrate by parts?
Yeah, you guys are dead. All right, you guys need to buck up on that strategy. All right. If you're curious, factor out the radical x, u substitution, u equals radical x, you get an arctangent at the end of the day. Right? Now, I'm playing this game along with you guys. Like I didn't pre-plan what I'm going to pick. But I can tell you what I would do, and I can tell you what's going to happen. There's going to be an arctangent somewhere. Like you should be able to see like 3 steps deep, like you're Bobby Fischer playing chess, right? That's where I want you to be. When you walk into test 1, you need to be able to look at any integral I give you. 3 to 5 seconds, you know how it's done. Now it's just, let me give Jhevon something to grade. Yeah, he's going to be bored. It's a formality. The integral needs to be dead by the time you look at it. Like, the integral needs to be afraid of you. Most people walk in their math test and they're afraid. No, the test needs to be afraid of you. Right? Because you're there to like kill the integral, right? So you're going to go home. You're going to go through the homework. You're going to go through the strategies I tell you. Then you're going to take this and every other integral you can find, and you're going to play that game. If you can't tell me within 3 to 5 seconds how to attack that integral, you need to study more. Every time you can't say an integral in 3 to 5 seconds, you have to practice 10 problems. Right? Another time you do it, practice another 10 problems. Right? So how many problems do you guys have to do now? Like 50, 60? No, but seriously, look, the power of that, you know what the power of this is? You could practice 100 integrals in 300 seconds. Right? And you know you'd be able to pull it off. Right? Imagine how you can practice without practice. That's going to be the game you're going to play. All right? Make it fun. That is time. I will see you guys tomorrow. Next time we're actually going to cover improper integrals. I'm going slightly out of order. I think the improper integral is going to flow a little bit nicer. So that's what we're doing now. Oh, you can keep. Some of you can take pictures, but I'll eventually do this.